Jnanam paramam dhyeyam. Knowledge is supreme.
Welcome to this course on Advanced Transition Metal Organometallic Chemistry. As the title suggests, this course focuses on various application aspects of transition metal organometallic chemistry. This course is a continuation of an earlier course that was run on NPTEL portal, and the title of the course was Transition Metal Organometallic Chemistry from Applications to Principles. Now, the earlier course presupposes certain concepts which are prerequisites for this advanced level transition metal organometallic chemistry course. And before we start talking about the content of this particular course, let me just reiterate what we had gone over in the last course, which was the transition metal organometallic chemistry from principles to applications. Now, as for the textbooks for this course, we will be following 3 textbooks. The first and the foremost is Organometallics by Christoph Eisenbroek. This is the third completely revised edition. It came out as in 2006, followed by another very important book in organometallic chemistry, the title of the book being The Organometallic Chemistry of Transition Metal by Robert Crabtree, 4th edition, John Wiley and Sons. And last but not the least, a book on organometallic chemistry right from India by Professor B.D. Gupta and A.J. Ilyas. The title of the book is Basic Organometallic Chemistry from University Press, and which came out in 2010. These 3 books will form the main skeleton for the course, and emphasis will be given on the first organometallic metallics by Christian Eisenbroek for the major part of the course. Apart from this, other contents in the web as well as any other book on the subject area will also be useful. Now, as mentioned earlier, that this course presupposes certain knowledge in organometallic chemistry, as this being an advanced level organometallic course, and that is why I would like to just mention the various topics that was covered in our earlier course. The course started off with a brief overview on the history of organometallic compounds, then looked at the reactivity and the types of organometallic compounds, particularly their classifications based on their sigma, pi, donor properties, the various kind of decomposition reactions, in particular beta elimination in sigma alkyl complexes as well as in transition metal alkyl complexes, and their utility in various catalytic applications were also looked at in our earlier course. Contemporary areas like CH activation, the characterization of CH activation and their bonding aspects were also covered. Not only the CH activations, detailed analysis were done on CC activations as well as CF activations, one of the most challenging bonds to activate in transition metal organometallic chemistry, particularly from the aspect of their high bond energies, particularly that of CF bond and CH bonds. These activation reactions were covered. The challenges in these activations, mainly in their selectivity, were also looked at. Apart from this transition metal sigma alkyl complexes that involved various kind of activations of carbon, fluorine, carbon, carbon and carbon hydrogen single bonds, the course also looked at metal-ligand multiple bonding and their chemistry. In this respect, worth mentioning are transition metal carbene complexes, the two famous ones, the Schrock and the Fischer type carbenes, and their reactivity, the reason for their particular reactivity, the nature of bonding in these compounds were also looked at. Not only the carbenes, transition metal carbonyl compounds, carbonyl migration reactions, carbonyl metallates, metal halides, and their applications, all these things were also discussed. A large part of the course was also dedicated to looking at the transition metal olefin complexes. These are very important class of transition metal compounds, as they give rise to reversal of reactivity, reversal of polarity that arise from Umpa-Long reactivity. So we have looked at transition metal olefin complexes. Not only that, we also looked at transition metal diolefin complexes, transition metal alkyne complexes, and their reactivity. Now, with this background being covered in the last course, this course sort of takes off from where we had left in the last course and looks at the more advanced level of this chemistry. Now, in particular, in this course, we are going to look at various kinds of interesting ligands. We'll start off with sigma donor pi acceptor ligands. These are ligands which are very interesting in the sense that they not only can donate electrons but also can accept electrons in their interaction with transition metals. These are hallmark of transition metal organometallic chemistry, where ligands are not just spectator entities which just donate electrons onto the metal, but in process it can also absorb electron density back from the metal, and that give rise to these famous pi acceptor attributes of these transition metal organometallic compounds. So we are going to look at allyl ligands, C3R3+, C4H4 ligands, then the famous cyclopentadienyl anyl ligands, C5H5-, they are nitrosyl and the hydride complexes. We are going to look also at B-serine transition metal complexes as well as the C7H7 ligands, C8H8 ligands, and their metal pi complexes of heterocycles. Now, with this, we would sort of come to an end of various kinds of ligands that we looked at in transition metal organometallic chemistry and enter into a domain of a very exciting realm of homogeneous catalysis. Actually, transition metal organometallic chemistry plays an important role in various catalytic transformations that has been carried out lately. And of them, transformations like CC cross-coupling reactions, including Heck, Suzuki, Steele, Sonagashira, and many other involving palladium, has lately been rewarded with the recognition of receiving this Nobel Prize. There are other reactions which would also be looking at, for example, hydrocyanation reactions, carbon heteroatom coupling reactions, hydroamination reaction, hydroboration reactions, hydrosilylation reactions, olefin oxidation reactions. For example, Fischer-Tropsch synthesis, carbonation of alcohols, and hydrogenation of alkenes. Now, these reactions has tremendous implications in industry, which led to preparation of various kinds of specialty and fine chemicals in large scale, and the source of these reactions fully lies on the organometallic compounds that often are used as catalysts for carrying out these reactions. Not to mention of the fact that last 7 or 8 discoveries in the last century can be traced to organometallic compounds and have been awarded, recognized with the Nobel Prizes. Now, as I mentioned or have been mentioning all throughout this introduction, is the fact that organometallic chemistry is indeed a very formidable science and is known to have made significant impact in the society, in chemical at large, and in chemical industry as particular. And there has been a tremendous amount of translation of laboratory chemistry to the industrial world, and which had been possible because of organometallic chemistry. As I have been saying that in the last century or so, about 8 or 9 Nobel Prizes have been awarded to the field that that speaks highly about the utility of these transition metal organometallic compounds. So the buzzword for transition metal chemistry is thus this translation. The translation of laboratory reaction to the industry scale reaction is what makes transition metal organometallic chemistry so interesting and so important to the society at large and chemists in particular. Now, in the last 5 or 6 minutes, I have painted an overview of this advanced transition metal organometallic chemistry course that I will be talking about, and it gives you a brief overview of the topics that would be covered, what would be the focus of this course, which particularly would be on the application aspects of transition metal organometallic chemistry. Now, the big thing about transition metal organometallic chemistry is the fact that many of the reaction have gone past the confines of laboratory and ended up in industry, and had resulted in blockbuster processes where billions and tons of many of the chemicals have been produced in industry using transition metal organometallic compounds. And that is why this subject becomes so very interesting and important. Now, with this with this introduction, let me just now start with various kinds of allyl and enyl type of complexes that we are going to be discussing as a part of this first lecture. Now, these allyl and enyl ligands are of the formula CnHn plus 2, and these are unsaturated ligands having odd number of hydrocarbons. So that means that, for example, N can be 3, so C3H5, N can be 5, so that is C5H7, N can be 7, so that means this is C7H9. Now, these are odd numbered ligands and their structure is as follows. Now, these ligands can exist in neutral form or charged form. The charged form can be anionic or cationic. I will illustrate some of the diagrams over here. For example, in the neutral form, C3H3 can exist as a 3 electron donor. This is in the neutral form. in the anionic form, C3H exists as an anion. So this is a 4 electron donor. Similarly, C5H7 can also exist in a neutral form. So it becomes 5 electron donor. They can also exist as an anionic form. Which makes it a 6 electron donor. Similarly, a 7 electron neutral form. Anionic form will make it a 8 electron donor. Now, what is important over here, that these ligands provide a wide range of ligands having electron donating capacity, which can range from 3 electron donor to 8 electron donor. Now, each of these ligand can exist in neutral, anionic as well as cationic forms. For example, the 7-member C7H9 can also exist in its cationic form, where it becomes a 6 electron donor, and this is the cationic form. And if the C3H5 becomes exist in the cationic form, then it becomes a 2 electron donor. So what is important to see is this allyl and enyl complexes provide a wide whole range of binding capabilities of the ligand in terms of their electron donation. Each of these ligand can exist in 3 forms: neutral, anionic and cationic, and as a result they have versatility in with respect to the electron they can donate. For example, C3H5 can donate 2 electron as a cation, 3 as a neutral, 4 as an anion, and so on and so forth. Each of these ligands, C5H7, C7H9, they can donate 3 types of ligands depending on which form they are binding. Another important correlation is that the neutral species are all odd electron donors, and the anionic and cationic species are all even electron donors with respect to their pi orbital. So this is a very interesting correlation about various type of allyl and enyl ligands that are out there, and the type of complexes they make with the transition metal. Now, one thing which is worth mentioning is in the radical form, that means that the neutral form of these CnHn plus 2 ligands, the neutral form, the radical form is extremely reactive given the fact they are radical, whereas the ionic ones, the anionic and the cationic ones, can be stabilized with respect to their salts of alkali, alkaline earth or transition metals. So, here we see that these anionic or the cationic ligands, when they complex with transition metals, they get more stabilized than the neutral form, which are just radicals which show very high reactivity. Now, having seen how these the ligands are the structure of them with respect to their electron donation, let us see how these ligands bind to transition metals. So, these transition metal allyl and enyl complexes can be written as or shown by so this is eta 3 allyl or C3H5 ligand. Similarly, so this is eta 5 pentadienyl. C5H7. Okay. Now, we are very familiar with the other C5H5, which is cyclopentadienyl, where this ring is sort of closed. So, many people tend to call this C5H7 or eta 5 pentadienyl as open CP ligand. So, as if the cyclopentadienyl ring is not closed and it's open, and that's why people call it open CP, or more appropriately it should be called as eta 5 pentadienyl ligand. Similarly, there is C7H9 which binds as this is called eta 5 cycloheptadienyl. Or C7H9, and as for C8H9, this is called eta 7 cyclooctatrienyl ligand. So, these as mentioned earlier, that these transition metal alkenyl complexes and allyl complexes are remarkably inert in contrast to their ligands. So, these transition metal allyl and enyl are inert as compared to their ligands, neutral form, because the neutral form has a radical structure. Now, we are going to look at a very interesting aspect of these ligand, particularly the metal-ligand interaction for transition metal allyl complexes. So, in transition metal allyl ligand. Now, this transition metal allyl ligand has 3 molecular orbitals containing p orbitals, and they are of psi 1, psi 2 and psi t 3 symmetry. So, let me just draw it over here. This can be thought of as psi 1, psi 2, psi 3. Now, these is sort of the homo, non-bonding, anti-bonding, bonding, MO, non-bonding, anti-bonding. Let us take a look at the metal orbitals which interact with these various kind of orbitals. For example, the metal component will be S or PZ, and dz square. Similarly, psi 2 would be interacting with Py of metal, and dyz of metal, and psi 3 simultaneously can interact with Px and dxz. Now, if one considers this interaction, what transpires out is that psi 1 to metal is a sigma interaction. This is ligand to metal sigma bonding interaction. Psi 2 to metal is a pi type ligand to metal pi type interaction. On the other hand, metal to psi 3 is a pi type metal to ligand pi back donation. So, this gives a very important picture about how allyl ligands interact with the metal. So, it shows that there are two bonding interaction, ligand to metal sigma bond, ligand to metal pi bond, and metal to ligand pi back donation. So, with this we come to the end of today's lecture, which had primarily been on looking at various kind of allyl and enyl ligands that are out there, how they interact with the metal, and what kind of orbitals from the ligand interact with the metal, and which would help us try to understand the reactivity of transition metal allyl and enyl complexes. So, we have also given overview of what is coming in terms of the topics that will be covered in future lecture. I thank you for being with me in this particular lecture, and look forward to discussing with you some more interesting and applied topics of transition metal chemistry, organometallic chemistry, that in the future discourses of this course, and which I think you would really be excited about. So, with this, let me thank you once again for being with me in this lecture, and I look forward to being with you in the next lecture. Thank you.